We're going to start a series of short videos on columns and column behavior. To begin with, defining a column, we want to talk about a member that's been loaded axially and normally in compression. We've seen this before for loadings normal to the cross-section of the beam. And usually we see columns vertically loaded. Columns come in all shapes and sizes. Here you can see we have regular columns for the bottom story of a building. Each one of these infills is also a column. The entire member itself is also a column with loadings at each of these different intersections where the floors are. And you can see that if you infill with a wall or a floor in between them, you create conditions that are very different from the other ones. That these are short columns and those are going to behave very differently from a regular column. We'll talk about that more in a little while. So far, we've been exposed to loading members in both axial and compression, as well as bending loads. But now, what's the difference between this type of axial compression load and columns is, in theory, nothing, except we're going to start talking about the behavior of these members when they experience an axial compressive load that results in a lateral sideways force. We call this buckling. Buckling occurs when this axially loaded compression member is loaded to a point where it experiences an instability, a structural instability, and a sideway motion, causing the member to bow out. Buckling is a behavior. It's neither good nor bad by itself, but it's a behavior and a phenomenon that, depending on where it's exhibited, can either be catastrophic or it can be used for good. Here's some examples. For example, natural disasters like earthquakes can call what's looking like here as bad buckling. These failures are usually catastrophic. This one happens to be from the Northridge earthquake in California back in '94. And of interesting note, these types of failures where concrete columns exhibited this explosion and of the reinforcing steel bumping out of the column and failing the entire member. This is what changed building codes to start requiring stirrups. This is another example of earthquake loading. Earthquake loading is random movement in all three dimensions. This particular image is interesting because the buckling occurred in a lateral action. Very little vertical movement or damage was seen here. On the other side, we can look at what could be termed as the good, or using buckling in engineering situations in design for the purpose of saving lives. Buckling can be used to control the failure mode. Okay, so in this case, the car hood is designed to buckle during a frontal impact before the hood hinges shear off. We can sometimes say we're designing a fuse, something that will fail so that another system will not fail. So in this case, what would happen for a minivan if the hinges sheared off before the hood buckled. This buckling is protecting the people inside the minivan. In this case, however, we're just saving the technician reassembly time because the crash test dummy, made it through just fine. And so this one here is a piston. When our engines exhibit or have a buckled piston in it, sometimes we call this a bent rod. So I'll leave it to you to decide whether or not this is a good thing or a bad thing. Dr. Prinz has the interesting point that if it's a car in a race and this happens to be your engine, then this might be a bad type of buckling. But if this happened in the engine of your competitor, maybe you would feel differently about it. We can model buckling mathematically using a relationship that was provided to us by a man named Euler. Oh, it looks a little goofy here. I'll go ahead and fix that. And so we can call the behavior of this particular type of buckling as Euler buckling. Okay, so here is our particular equation. We have what we call a critical buckling load. We will define this as the load at which structural instability occurs. I made a mistake there in my writing. It should be instability occurs and the column buckles. We call this P. You'll see that I made a little mistake in my writing here. The critical buckling load is the load at which structural instability occurs and the column buckles. We denote it with a capital P sub CR for critical. And we can see also that capital E modulus the elasticity of the column material. We already know that. I is the moment of inertia of the column cross-section. And we also need to know what the length of the column is. Now, notice that this column length is squared, which means that the load at which this instability happens, that we have failure, is inversely proportional to the square of the length. So when the column gets longer, our load capacity to carry load is reduced very quickly. Let's take a look at some of the assumptions involved with the Euler buckling load equation. Mr. Euler derived this equation based on the model you see here. The pinned condition on the bottom was considered common or normal at the time, and the condition at the top. Sometimes people refer to this as a pin, but it's much more like a roller. Because the column is only constrained in the lateral direction here at the top. It can still move vertically and it still is released as a moment because this is a pin. This column experiencing the vertical compressive load shown on the right will have the propensity to buckle once the critical buckling load is reached and the structural stability occurs. When the column is loaded and PCR, the critical buckling load, is reached, the column will be structurally unstable. If the column is perfectly loaded and undisturbed, and it will buckle if disturbed. In reality, the perfect loading and undisturbed condition is not possible to exist. And so we know that once the critical buckling load is reached, the column will buckle. So this begs the question, how might we prevent or resist this behavior? We could add a side load somewhere along the column to resist the buckling. Which could get larger as the displacement gets larger. Often we will look at this as a spring in equilibrium with a spring constant K with units such as pounds per inch. And as a result, as the displacement of the column occurs, the value of the responsive spring force will increase. And if we do this, then the matter becomes how much resistance is needed to prevent buckling. How big of a spring or spring constant do we need? The answer, it turns out, is about 2%. 2% of the axial load generally will prevent buckling. It's not much, but it needs to happen to prevent the buckling. So let's go ahead and wrap this short video up, and we will go on to the next video to work some example problems. Thanks for listening.